Hello everyone, welcome to the P102 lecture. This is the second lecture. The first part has completed. First part we discussed about units, right? Now in this part we are going to discuss in detail about dimensions, and we are going to start with dimensions here. Anyway, what are dimensions, right? We have gone through units and we have also mentioned dimensions. If you have a table like this, right, you can use the dimensions of the height, you can use the dimensions of the weight, right, you can use the dimension of thickness, you can use several other dimensions as well. You can use material density, you can use material quality to compare. So anything you can use to compare with something, and you can get some feedback from that, that's called a dimension. So that's a measurable, anything measurable is a dimension, right? So with this part, now if you look at a person, you can look at a person and you can see dimensions anyway. You can look at his face and you can see the height of that person here is a dimension, the size of that person is a dimension, the eye color is a dimension, his mouth, his ear size, that's a dimension you can use to compare with another one, right? So that's a dimension you can measure and you can represent in terms of some number or some metric. That's called a dimension. You can use that information in terms of some number, then that's called a dimension. Now that thing aside, i'm going to use I'm going to in physics, as you can see, there is a lot of use of dimensions. We represent every equation with the left side and the right side, and both side has to have some equation, right? So it has to equate on both the left hand side. That means the dimensions have to be same on left and right. It cannot be different. You cannot have apples here and mangoes here, right? That's the basic expression you hear most of the time. So you cannot have apples and mangoes on different sides. That means they have both to be equal, right? So how can you make sure that they're both equal? And what's the use of making it equal? So if you look at the dimension of an area, it will be L square. So dimension of a volume will be equal to L cube, right? That means that if you consider a square space like some length and length, that means the area in between is called L square. And if you find L cube, that means the volume will come into place. So you are adding dimensions to it with each L square L cube term. So that's how dimensions work. Okay, when you multiply them, you get a bigger dimension, bigger attribute. Now with that, I'm going to use the principles of dimension. This is the principle dimension analysis to find out something very abstract, right? If you have something like an apple hanging over the tree, and you look at the ground and you see that this apple is going to fall down. So there is a height with respect to the apple, and then there is a mass of the apple, that's the dimension. Then you have the maybe the thickness of the apple, it's all right, it's not significant. You can find the time for that apple to reach the ground, that's a big dimension, right? And you can use the force with which the apple is attracted. So it's going to travel in some velocity downward, so there is some velocity involved. There will be an acceleration, as you know from the 7th class. You've been studying the Newton's gravitational force. So it will be attracted downwards, and then there is an acceleration inward. So you know that acceleration is equal to v2 minus v1 by t. That's the basic equation of acceleration. So you know that it's directly connected with velocity, so we don't need to introduce velocity into this dimensional analysis. So we have acceleration, that's enough. Now I'm going to use this concept, this falling of an apple from a tree, to mitigate the to evaluate the time. Okay, how much time does it take for the apple to fall from that height? So let's assume that time, let it be, time will be dependent on some factors, right? The time increases as the height increases. Time decreases as the so the time increases as the height decreases. So time will be dependent on height of that apple. Maybe it will depend upon the what say the mass of the apple. If the mass of the apple is large, it could take longer time. Is it possible? I'm asking you as a question. It could be possible. Is it based on our level of knowledge right up until now? It could be possible. Well, we'll see what will happen. And it could also depend upon the acceleration, right? So if the acceleration is high, it could fall faster, right? It could go fall faster, so it will be depending upon the acceleration. Okay, they are depending upon that. It won't be equal to that, so let's write it's proportional. So proportionality is basically if you have something like an x here, and it's proportional to y, that means x increases, y increases, x decreases, y decreases. If x is inversely proportional, this is like that, then x increases, y decreases. Also x decreases, y increases. That's called a proportionality. So anything that is proportional is directly or indirectly proportional. That means it's increasing in one side will increase the other or decrease the other. That's called a proportionality. So with that as well in place, now let's look at our case. What will happen in our case? Okay, let's look at this in the time. It's impossible for us to calculate this without basic usage of equations of motion, the Newton's laws. Without that we cannot calculate the time, right? It's not easy. So is it possible for us to use the time to measure this relationship, if it is true or not? Okay, let's do that. Okay, let's write down the dimensions of each side. Okay, each side has different dimensions. So it's one here, it will be the height, which will be L. So the mass will be M, and also the acceleration, right? Acceleration will have this unit, let it be. So you can write down the acceleration will look something like, acceleration will be different, like acceleration has change in velocity with respect to time. So that means it's the dimensions of velocity by time. That means it's has the dimensions of L by t square, right? So that's the dimensions of acceleration. Ooh, 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 ooh. Okay, we don't know how much it is directly dependent, so let's put down some exponents. So let it be alpha, beta, and gamma. We don't know how much is it dependent on, so we are going to put some power. So it could be L square, it could be m square, it could depend upon L by t square the whole raised to the 3 by 2, whatever. We don't know the dependence, we need to find out the dependence. Okay, let's use this to find out the dependence. Now how can we use that? So we in this left direction you have t, which is of power of 1, and in the right direction you have L, which has two values here. So it's alpha plus gamma, right? And m has the power of beta, and t has the power of minus 2 gamma, right? It's in the denominator here, so it's minus 2 gamma. Okay, now on the left side you have only t, so t is equal to like that. So that means you can straightly correlate, this is t is equal to raised to 1. In this side m has no exponents, that means m raised to 0 is in this side. So that means you can now correlate the exponents, and you can say that t raised to 1, so it's 1 is equal to minus 2 gamma, or you can simply say gamma is equal to minus 1 by 2. And also you can now use L raised to alpha plus gamma is equal to L raised to 0 in this side. That means alpha plus gamma is equal to 0. We have already found out the gamma, that means you can use alpha is equal to 1 by 2, right? You can equate and you can find out that. So we got alpha gamma and beta is equal to 0 because there is no mass term in the left side. So we got alpha, beta and gamma. So T is proportional to, so T is proportional to some height raised to 1 by 2, mass raised to 0, right, alpha, beta and gamma. The acceleration is acceleration due to gravity, right? You've seen that is the value is 10 or 9.8 if you want to be precise. So it's 9.8 meter per second or 10 meter per second on average, or approximating. So g will be raised to what, gamma, right? Gamma is here, it's minus 1 by 2, so it's minus 1 by 2. So that's a very promising relation. So if you are very compliant enough, you can see directly that t is not depending on mass. So the heavier the object, the lighter the object, bigger the object, smaller the object, if it is dropped from the same height, it will fall to the ground. If it is okay from the same height, it means this is not a proper way, right? From the same height means like this. If you can drop two things of different mass from the same height, it will fall down to the surface in the same time. So it is mass independent. We have found out that from dimensional analysis. Okay, that's the first thing. Now the second thing is that it is proportional to the square root of height. So that means time will be equal to some constant. I don't know what the constant is. We cannot find constant numerical constants out of dimensions. So some constant times square root of h by g. Oh, that's very good. That's very good. So you can say that time is proportional to root of square root of h by g, right? That means if there you are keeping an object from the falling, keep dropping an object from the height of let's say like 2 meters, 4 meters, you get 2 by g. That's 2 by square root of g is the time, or around 2 by 3. If it's from 8 meters, right, or let's say 9 meters, it will be 3 by root g. So a particle dropped from, or if it is 16 meters, it's easy to analyze. So if it is 16 meters, that is, if you drop an object from 4 meters and 16 meters, right, 4 meters and 16 meters, you will consume more time, right, double the time. So if it is for dropped from 4 meters, you get 2 by root g. uh, then for 16 meters you get 4 by root g. That means it's almost double the time. So the ratio of time for double the distance is very not that directly, not that direct, straightforward. It won't be twice, it will be 2 by, or the distance, the square root of distance by root of g. So that's a very easy way of representing. So we know the ratio of time for t is equal to 16 by t is equal to 4 without actually doing any more than dimensional analysis. So we know that ratio, straightforward, right? It's easy, right? Right there, it's right there. Now with that aside, I can, okay, I hope you understand the importance of dimensional analysis, and I hope you are convinced enough that we can use dimensional analysis to find out complicated stuff right out of nothing, right? You don't need to go through all the complications, but you can actually make a measurement based upon this experience. So we know that when you drop something from 4 meters and 16 meters, it will take twice, right, for 16 meters. So that's a straightforward answer you got out of nothing without any more calculation. That's a very big advantage of dimensional analysis. That's second advantage of dimensional analysis. We had one advantage here, so there's second one we have found out. And the third one is that if you have, like, say, uh, area on this side, that's meter square, you cannot have uh, something like a meter cube or meter by time or meter by length or anything like that. You cannot have that kind of an equation. It is unstable, it is impossible. That means when you see an equation like say say let's say what a is equal to v by t, let it be this equation. Is it right? Or say a is equal to vt, which one is right? That's a question, right? You can analyze this using dimensions. So a has the unit of meter per second square, and v has the unit of meter per second times by second will be seconds, right? And this is a right equation. Is it the perfect equation? Is it the most suitable equation? Is it the precise equation? It won't be possible. It cannot be the right equation, but it can be a true equation. It is possible. But this one, when you look at this one, you have meter per second square, which is equal to meter per second times second, which is equal to meter. This is an impossible equation. So if you see such an equation, you can straightforward write down that this equation is not possible, it is not right. A cannot be equal to vt, right? But this equation is possible. That's that. It couldn't be right. In real case, a is equal to u plus at. Sorry, we you can write v is equal to u plus at. So you can write it like that, and you can compare that equation. This is a direct equation for velocity. We will discuss that later. So this could be a real equation, but it wouldn't be the right equation, right? If u is equal to 0 here, we can write down that a is equal to v by t. You can write it like that. If u is equal to 0, that's the case. That's a typical case of this equation. uh, Equations of motion, one of the equation of motion, we'll discuss that later. But this could be a real equation, but this is not a real equation. That's straightforward from dimensional analysis. This is an important part of this lecture series. This is a basic foundation part, and I want you to understand this thoroughly. Okay, I need you to use this equation in different parts, and see it for yourself that how important this is. Okay, with that, I'm closing this lecture. See you next time.